Hello again and welcome back to the Energy Onion, Energy Systems Engineering Training Certification, Chapter 5. With the first 4 chapters behind us, you'll begin to see that they were indeed the largest with respect to content, and we're beginning to now get into what are some minor chapters. Not with respect to sophistication or application. These aren't minor topics. But in the context of the Energy Systems Engineering certification, the breadth of material within, for example, industrial systems, is narrower because of what we expect you to be doing with the information. Indeed, any of these chapters 5 through 12 can be a study in themselves. But for the context of this certification, we use them to round out the technical information. So enough introduction. Let's begin with industrial systems. When we use the term industrial systems, in our context what we mean are boilers, steam systems and their requisite condensate systems, waste heat recovery, and compressed air systems. These definitions are most appropriate for the first 3 of those 4 systems we'll discuss in industrial systems. That is, boilers, steam and condensate systems, and waste heat recovery. Let's begin with the gauge pressure. Gauge pressure is what you think it is. It's the pressure on a gauge in a regular circumstance. It does not account for or compensate for the atmospheric pressure. Absolute pressure, on the other hand, is the gauge pressure plus 14.7 pounds per square inch. That is in addition. That is the pressure that the atmosphere provides. The BTU, or British Thermal Unit, is in the United States a point of calibration for unit and dimensional analysis, getting units of energy into BTUs. Specifically, it is the amount of energy needed to heat 1 pound of water 1 degree Fahrenheit. The boiling point, it is not 212 Fahrenheit or 100 C. It's more complicated than that, particularly in these systems, as it is dependent on temperature and pressure. Its definition is it's the temperature at which the vapor pressure of the liquid equals the pressure in the atmosphere around the liquid. Now let's consider saturated steam and superheated steam. We'll have a graph in a few slides that illustrate these as well. But just consider, as you have a pot of water and boil it, the temperature of the water can get to a maximum point, at which point the water evaporates. It becomes steam. But at some point, the water has all evaporated and you have all steam. But if you keep heating it, you can superheat it. So those are the 2 circumstances, saturated steam and superheated steam. And the dividing line is when the last drop of water is evaporated. Sensible heat and latent heat we've discussed as well in the HVAC section. But think of it this way. Think of sensible heat, sensation, sensing, feeling. It is the felt change in temperature. The latent heat is heat that causes a change of phase without a change in temperature. You'll see that on the graph as well with saturated and superheated steam. But sensible, the change in temperature; latent, the change in phase. Remember that. Enthalpy, for our discussion, we will avoid the chemical engineering course in enthalpy and just call it the internal energy. When we say enthalpy, we mean the energy internal to the compound we're discussing. Specific volume, think of it in terms of density. It's indeed the reciprocal of density. It's 1 over the density. But when you think of specific volume, think of it as a measure of density. Units of specific volume would be, instead of pounds per cubic feet, would be cubic feet per pound. Instead of grams per cubic centimeter or kilograms per cubic meter, it would be cubic centimeters per gram or cubic meters per kilogram. The condensate in these systems occurs when there's a change in phase from gas to liquid. It's the opposite of evaporation. What happens is, as something cools or otherwise lowers its molecular energy, these billiard balls of, say, water molecules that used to be separated as gas are now collecting. They're condensing because of their lower energy. And then flashing, or partial evaporation, is a technique used where you can put a stream through a reduction in pressure, pass it through what's called a throttling valve or some kind of device like that, and you can take hot water and put it through a valve, decreasing the pressure, and the water will flash into steam. It will immediately become steam. Remember that the boiling point is a function of temperature and pressure. So you can take hot water at high pressure, put it through a throttling valve, and create steam. And you can do a lot of useful things with steam. You remember these two boiler pictures from the HVAC section as components of an HVAC system that create hot water to do space heating. And just briefly, we'll go through these cartoonish pictures again, but unlike in HVAC, we will here go the second step and look at some of the componentry of boilers. The most obvious thing we discussed earlier was the difference between water tube and fire tube. Water tube simply means the water is in the tubes, and in a fire tube, the fire is in the tubes. You can see how this would affect the generation of steam and the use of the heat to generate the steam. But again, there's a lot of simplification here. So let's look at the next slide that presents more of the technical detail of boiler configuration for the industrial systems section. Well, the first question based on the last slide is this a water tube boiler or a fire tube boiler? Look at the configuration. Look at the water coming in, and the water goes up through the tubes and the fire is outside the tubes. So this is a water tube boiler. But then let's look at the function of the boiler. The water comes in through an inlet in the lower right corner into what's called the feed water drum. That's the circle on the bottom right. Up towards the middle, the bigger circle, is the steam drum. The feed water, it's drawn up as it heats up by passing through the boiler tubes and the heat surrounding the boiler tubes. It bubbles up into the steam drum, and it separates in the steam drum into steam and water. The water comes back down through the downcomer tube and back into the feed water drum. The steam then comes off the top of the steam drum and can go through what's called a superheater. Remember, the only thing in the superheater is steam. So when you heat steam, what do you get? You get superheated steam. That's right. As one considers the efficiency of boilers, of course, as you know, the component itself, the boiler itself, the design, the materials of construction, and so forth, have a lot to do with the efficiency of the boiler. But there are some things that, given a boiler, you can operate it more efficiently. You can maintain it as well. to operate more efficiently. The first boiler efficiency we have added here is what's called excess air. As you look on the horizontal x-axis on the graph in the lower right, you see excess air on the right, excess fuel on the left, but a vertical line that says stoichiometric combustion. What this means is that if you were to write out the chemical stoichiometry, the chemical equation of the combustion of this fuel, there would be a point at which exactly the right amount of fuel and oxygen had been burned. You didn't have any extra fuel, you didn't have any extra oxygen. What this graph also shows is a gold line, carbon monoxide. There is a place at which there's just enough excess fuel that you have a maximum of carbon monoxide. And of course you want a minimum. So what do we call our highest efficiency? It's there in the gray bullet-shaped region as well as plotted in the red. And it is where excess oxygen and excess fuel and the emission of carbon monoxide, where all three of them come to a minimum. Because indeed, when you run the boiler, you tell the boiler how much fuel to use, how much air to use. It's no different than the combustion engine on your car. So you have to set those to get the highest efficiency. Exhaust stack temperature is a measure of efficiency. It's a measurement that allows you to check and maintain the efficiency of your boiler. Waste heat steam generation. If you can generate, or if you are generating waste heat somewhere in your process and you can use it to help generate steam, you will improve your boiler efficiency. Load balancing just means balancing the load, the requirement for hot water, for steam, whatever you're using your boiler for, to balance the requirement for that with the production of that. Boiler blowdown, as you continue to evaporate water through steam, you evaporate pure water. Much like in the cooling tower, you evaporate pure water. What's left is water that has more hardness, more corrosion-causing elements in it. And so you use your boiler blowdown, just like your cooling tower blowdown, to remove that most concentrated water in the boiler. And then lastly is your condensate return. If you can return the hot water, the condensate that forms in your boiler process lines, if you can return that hot water to your boiler, well, that's less cool water, cool fresh water you'll have to provide. So all of these things will improve boiler efficiency. Finishing the previous slide on a boiler, we're going to start the next industrial system, the steam and condensate system, starting with its beginning component, the boiler. The boiler has the same function as steam and condensate system, followed by the feed pump, which you saw on the previous slide, is that which feeds fresh water and condensate back into the boiler. The economizer is a new term. It's a component of a steam generating unit that transfers the heat from products of combustion after they've passed through the steam generating and superheating sections to the feed water. So now you have feed water that can come in a little hotter and save a little energy. The next component on the steam and condensate system is, say for example, a shell and tube heat exchanger. There's some purpose you have in your industrial process for extracting heat from the steam. You maybe use a shell and tube heat exchanger. And then when the steam is used up, or its energy is used up and it condenses back to water, you see it goes through the steam trap and back into the condensate line. The steam trap that we mentioned briefly earlier is the device that allows water to get through but not steam. You can imagine if you had an open pipe, you'd have steam and water getting through. All you want to get through is the water. The next typical component, these aren't on every system, but a typical component is a pressure reducing valve. Maybe you have steam at a certain pressure that you need it at a lower pressure. So you use a pressure reducing valve, you have a process heater on this end, some other use for the steam. And then lastly, once the steam has been used, high pressure steam on the boiler side, low pressure steam as you get further and further away from the boiler, once all the steam's been used and recondensed, you have a condensate pump that pumps all the condensate back to the feed pump and through typically a deaerator to prevent corrosion and so forth. This is the interesting graph that we referred to earlier when I said the difference between saturated steam and superheated steam. I mentioned that with sensible heat, latent heat, that we'd see a graph later that gave you a visual to those definitions. Let's say, for example, you have a liquid, and as you heat that liquid, the temperature goes up. At some point, it begins to boil, and the temperature stops going up. Boiling water is 100 degrees C, 212 Fahrenheit. It doesn't get hotter. The energy of the system increases, but the temperature does not go up. At some point, you now have only vapor. You have heated it to the point where all the energy in the heating has converted all the water or liquid into vapor. What this next set of lines says is what would happen if you increased the pressure. If you increased the pressure, it would take a higher temperature to convert the liquid into two phases, a higher boiling point. Those two phases then would continue as they do at the lower pressure, and then the vapor would become the predominant and only phase. If you do that again, increasing pressure, and again increasing pressure, and you see the pattern here, you'll create a curve. And what this curve defines is that at some temperature and pressure, whether you have liquid, saturated steam, which is the two phases, or superheated steam, is determined by its position on this temperature pressure or temperature enthalpy curve. Since that would be very difficult to interpolate data on that graph, we convert the graph into tables. This is a table of superheated steam. I use this because typically superheated steam also has saturated steam on it. Let's look at this superheated steam table and see how can we use this in a steam and condensate process. First, the axes. In the yellow oval, you see absolute pressure. And that's why we defined absolute versus gauge. You need absolute pressure. So if you have gauge pressure, you need to add 14.7 psi. At absolute pressure, the saturated temperature is listed below. And the temperature for superheated steam is listed in the blue oval. What that means by the saturated temperature, that means at that absolute pressure, the saturated temperature is the temperature at which the liquid begins to boil. It's the point at which it starts to become two phases. So let's look at an example. Let's say we have an absolute pressure of 15 psi, a little higher than atmospheric, which is just above it at 14.696. And let's say we're looking at beyond the two-phase region, we're looking at all steam that has been heated beyond 213.03. It's been heated beyond that two-phase region, outside of the top of that curve to 500 degrees. What we can know is from these superheated steam tables, we can interpolate what the enthalpy is in the specific volume. The enthalpy is the little h. It's 1287.3. And the specific volume is 37.985. Now what you do with those numbers and the units for those numbers, that's more important as you use them to calculate what you can do with that steam. Turning a turbine to make electricity and so forth. But just suffice it to say that the steam and condensate process produces steam with characteristics that can be looked up on these tables, and then the numbers where they intersect can be used to estimate the performance of things that use the energy in steam, say for example to create electricity. We have 3 slides on the third industrial system, this idea of waste heat recovery. The first slide here is definition and terms, and the next 2 slides are examples of equipment that provide for waste heat recovery. Indeed, the configuration and the mechanical system is used for a lot of purposes. In our purpose here, we'll consider them as waste heat recovery methods. The quality of waste heat, as you see here, high, medium, and low, has to do with the flexibility that you can have to use it in many different applications. Imagine if you had waste heat that was 3,000 degrees, you could do a lot of different things with that. If you have waste heat that's 200 degrees, you can do fewer things with that. The high temperature gives you flexibility. Some examples: a high quality waste heat could come from a refining furnace, a solid waste incinerator. All this heat that just goes out the stack can be used for something. Medium quality waste heat recovery could be from a steam boiler exhaust or a heat treating furnace. Low quality heat recovery can come from processed steam condensate. We saw that earlier. You have condensate from steam that was used for some process, and the temperature of the hot water, the condensate, is somewhere between 80 and 200 degrees. Or processed cooling water. There are various types of heat exchangers available. When you're considering equipment to recover the waste heat, they're often categorized, this equipment selection, consideration, so forth, they're often categorized by the medium of the waste heat. Is it air? Is it water? And the recovery stream, is that air or is that water? How are you going to get that waste heat out? And whether or not those two mediums are separated or they're in contact with each other. In addition, different equipment allows for mixing, which, if waste stream's contaminated, can cause you a lot of difficulty if the waste stream is mixed. Some downstream effects: if you're using waste heat for some purpose, there is a connection between these two processes that otherwise wouldn't exist. So be careful as you change a process that creates waste heat. If you're using that waste heat downstream, you're going to affect that downstream use. Although this may be a little bit of a repeat of the quality discussion, the types of waste heat can be exhaust. As we mentioned, a furnace exhaust, hot gases that just go out into the atmosphere or out into the complex, into the building. You can have condensate, as we mentioned, for the low quality. You can have hot water condensate from a steam recovery process. You can have drain water, water that's warm but not hot and would just go down to the city drain. You can put that through a heat exchanger and get the heat out of it to preheat something you would normally otherwise have to heat. And of course, solid waste. Whatever there is that's going to go in a landfill, as long as it's not hazardous and you can keep carbon monoxide down, you can burn it to create heat. And all of that would be waste heat. mentioning on the previous slide, we would have two additional slides showing configurations of waste heat recovery systems, and here's one. They called plate and frame heat exchanger. And the reason it's called plate and frame is because it's composed of these plates that are sandwiched together and held together with this, in this case, blue frame. We've highlighted in yellow how the flow in this cross-current plate and frame heat exchanger works. In this frame, in this plate, pardon me, the liquid would come in the top left hole, come across this metal surface where it exchanges heat with the liquid on the other side of that surface, and then out the opposite hole. So you see, when they're all stacked together, fluid comes in the top left hole and out the bottom right hole, and the other fluid in the other two holes. So indeed, in a plate and frame, none of the fluids mix, and there's a large surface area for this heat exchange to take place. Plate and frame heat exchangers are very, very popular. The next type of heat exchanger is a shell and tube heat exchanger. Look at the consistency with the appearance of the fire tube boiler. Indeed, a shell and tube heat exchanger, it could be a boiler, it could be an air conditioner. This configuration of a large shell filled with dozens, hundreds, thousands of tubes is a very efficient way to do heat exchange, where these tubes are surrounded on the outside of the tubes by one liquid with another tube running inside the liquid. Just looking at this picture, you can imagine the incredible surface area for contact, i.e. heat exchange, in this shell and tube heat exchanger. I guess it's worthy of a note to make a comparison that air compressors are similarly classified like chillers in the type of mechanical compression taking place. Is it a piston, a rotary vane, a centrifugal, a screw? And the picture on the bottom is just to show how, for example, a piston compressor works. Just like in an engine, and that's why these have gasoline engines or diesel engines or electric engines in them, you have to pull the piston down. When you pull it down, the diaphragm or the valve will open on one side, and then when you push it up, that valve closes and the other valve opens. So as this piston bounces up and down, those valves open and close, and you push air into this system, and more air, more pressure, and you get compressed air. The only reason for showing you this configuration is to highlight the potential for losses, malfunction inside the part of the system you won't normally see in the air compressor. This slide is a summary of the results of a group called the Compressed Air Challenge. It's predominantly manufacturers and their customers, manufacturers of compressed air systems. But in addition, state agencies and energy efficiency organizations, utilities, other groups, they came together to improve performance of compressed air systems. Now you'll see this adds to more than 100%, but what they found were half of the people responding to the survey had leak problems. 20% had piping configuration problems, receiver sizing problems, header piping problems, and 30% had control system problems. And of course, the reason they add to more than 100% is because many people had more than one or two or three problems. So there are indeed a lot of energy saving opportunities with such a simple system. Let's look at what that system really looks like. Although this is a little bit of a cartoon, it includes some important characteristics and components of a compressed air system. This would be often considered a single compressor system, although there are two compressors, because there's one receiver. As you look around this componentry, there are opportunities for savings. Leaks, piping configuration, all those things we just mentioned are all included and used on this type of system. And like 50% of the facilities that responded had leak problems, not only is it the most predominant problem energy cost with a compressed air system, it is also the largest dollar amount, as we'll see next. As you look at this slide, what you see on the left on the y-axis is leak rate, cubic feet per minute. And across the x-axis is supply pressure, pounds per square inch gauge pressure, PSIG. And the lines represent leaks of different sizes. So let's look at a process pressure, a supply pressure of 90 pounds per square inch on the gauge. And let's consider we had 10 leaks that were 1/16 of an inch and one big leak, 1/4 of an inch. Those leaks would total, by this graph, to 149 cubic feet per minute. But if we use reasonable conversions and electric cost, we can convert that 149 cubic feet per minute, not a lot, we can convert that into over $7,000 per 8-hour shift per year. Another case study on leak detection showed that a chemical plant found 160 leaks, saved almost $60,000 a year. The other thing to see off this graph is to look at the slope of the line. Look at the effect of discharge pressure on loss. So if you can reduce your supply pressure without even fixing the leak itself, you'll reduce the losses. Although this was the beginning of the mini chapters to complete the Energy Systems Engineering certification, we do cover technically challenging systems in boilers and steam systems, waste heat recovery, and compressed air. We present them, we believe, in a right size, sized for what you need to be a certified energy systems engineer. If you are in the boiler industry, certainly you're going to need more information than this. But that's the same for any of our modules. We're going to continue this with Chapter 6.